Welcome back to The Explainer, everyone. I am so thrilled you're joining me today because we are diving into a truly fascinating, high-stakes world of engineering, substation protection, and grounding safety. We're going to pull back the curtain on the massive, unseen systems, the complex math, and the physical infrastructure that keeps our electrical grid running and, most importantly, keeps us safe from just unfathomable amounts of raw energy. I mean, really, think about it for a second. When lightning strikes a high-voltage transmission line, or some equipment fails and causes a massive short circuit, we're talking about tens of thousands of amps of fault current surging through the system. Where does all that deadly energy actually go? If it's not managed absolutely perfectly, the results are catastrophic. So today, we're answering that exact question by looking at the life or death stakes of electrical fault currents. Here is our roadmap for today. We'll start with the grid's critical hubs, move into switchgear and fault protection, tackle the new renewable energy protection challenges, break down the physics of ground faults, look at tolerable current human safety, and wrap up with designing the ground grid. Let's get right into it. Section 1. The grid's critical hubs. To truly understand these massive electrical faults, we first need to see the big picture of the grid itself. Electricity is generated at power plants, or solar and wind farms, right? And then the voltage is stepped way up to push it efficiently across long-distance, high-voltage transmission networks. But obviously, we can't pump that kind of voltage directly into your home or business. And that is exactly where substations come in. They are the critical hubs where voltage is stepped down for local distribution. But because they handle such massive transitions of power, they are also the exact locations where catastrophic faults have to be managed and neutralized. Section 2. Switchgear and fault protection. So what actually acts as the grid's first line of defense against these catastrophic failures? First up, we have switchgear. This is a broad term for the substation equipment designed to operate outdoors 24/7 in literally all weather conditions. Switchgear has one primary job, and that's to safely interrupt massive amounts of power during abnormal conditions, like a lightning strike or a fallen tree, and isolate the faulty equipment from the rest of the grid. Now, the real heavy hitter in the switchgear family is the circuit breaker. Unlike a simple disconnect switch, a breaker actively extinguishes massive power arcs to isolate a fault. And sizing the breaker itself is a highly precise science that uses two distinct ratings, and honestly, confusing them is a super common error. First, you have the momentary or close and latch rating. This covers the very first current peak the breaker must physically withstand without getting damaged, dealing with that highly asymmetrical peak current. Then you have the interrupting rating. That's what the breaker must actually clear a few cycles later when some of the DC offset has decayed and we're closer to a symmetrical RMS value. To figure this out, engineers rely on the E over X method as a standard shortcut, basically applying a multiplying factor to convert a simple symmetrical fault calculation into a properly conservative asymmetrical rating requirement. But here's the thing, a circuit breaker is blind. It relies on a current transformer, or CT, to detect the massive fault surge and signal a protective relay to trip. And there are three main relay schemes that cover the overwhelming majority of protection applications. First, overcurrent relays. These are the simplest. They trip when current exceeds a set threshold, using a time delay curve that trips faster as current gets higher. Second, we have distance relays, which are heavily used on transmission lines. They calculate impedance to figure out the distance to the fault, using layered zones. Zone 1 covers most of the line and trips instantly, while zones 2 and 3 cast a wider net and trip with a slight delay to act as a backup. Finally, differential relays. These protect a very specific zone, like a transformer, by comparing the current entering versus leaving. If those numbers don't match exactly, it means there's an internal fault, and it trips instantly with zero delay. It's the fastest, most secure scheme available. You just have to match the scheme to the zone size and speed requirement. Section 3. Renewable energy protection challenges. That traditional setup we just talked about has worked beautifully for decades. But, as you know, the grid is changing rapidly. Integrating solar and wind power completely changes how we detect these faults. Traditional power grids were built around synchronous generators. Think massive spinning turbines with high inertia that naturally resist sudden changes and pump out a really high, easily detectable fault current. But renewables, they're inverter-based resources. They have super low inertia, drastically reduced fault currents, and they create a bidirectional flow of power. This throws a massive wrench into traditional protection coordination. If that fault current is too low, those relays and circuit breakers might not trip fast enough, or honestly, they might not trip at all. Section 4. Physics of ground faults. Let's shift our focus to the physical environment. What happens when all that electrical energy gets dumped into the earth? Under normal conditions, the ground beneath a substation is sitting pretty at zero potential. But when a fault occurs, the system intentionally dumps thousands of amps of current into the earth to clear it from the wires. Now, because the soil naturally has resistance, dumping that much current causes an instant, deadly spike in voltage known as ground potential rise, or GPR. Essentially, the literal dirt you are standing on suddenly becomes electrically charged relative to the remote earth around it. So here's the crucial point. Ground potential rise itself isn't what kills you. It's the difference in potential across your body that does. If you take a step and one foot is on soil at 5,000 volts and your other foot is on soil at 4,000 volts, well, that 1,000 volts of potential difference is going to travel right up one leg and down the other. That is called step voltage. If you touch a grounded metal fence while standing on charged soil, that potential difference travels through your arm and down your legs. That's touch voltage. So walking step by step through the exact sequence of a fatal accident, it looks like this. First, a high fault current goes to ground. Second, the resistivity of the specific soil creates high potential gradients right at the surface. Third, a person happens to be standing there and bridges 2 points of high potential with their feet or hands. And fourth, because there's no sufficient resistance, like specialized insulated boots, to stop it, that current flows directly through the human body. Section 5, Tolerable Current Human Safety. This brings us to a somewhat sobering but absolutely vital area of study. Exactly how much current can a human body actually survive? What's really fascinating is how we even got our safety data. Decades ago, researchers had to figure out the threshold for ventricular fibrillation, which is the point where an electrical shock causes the heart to lose its rhythm and fail. They conducted extensive testing on animals of various weights, like calves, sheep, pigs, and dogs, as you can see mapped out here. This foundational data allowed the IEEE to establish highly rigorous, mathematically sound safety thresholds for human beings, based entirely on body weight. Taking that data, engineers literally used 2 standardized human body weights to calculate the safety limits of the entire power grid. They designed for a 50-kilogram person, which represents a smaller adult or worker, using a mathematical constant of 0.116, and they calculate for a 70-kilogram person, using a constant of 0.157. These constants are absolutely essential because they help engineers calculate the absolute maximum safe fault duration a person can withstand before going into cardiac arrest. Which brings us to Beagle-Meyer's Z-curve. This curve visually proves that survival is mostly a race against time. Notice how, as the duration of the shock decreases, the amount of current a human can tolerate before fibrillating goes drastically up. If those primary relays and circuit breakers we discussed earlier clear the fault in just a few milliseconds, a worker standing in that substation can survive a significantly higher voltage spike than if it took a full second to clear. Speed is quite literally a lifesaver here. Section 6. Designing the ground grid. So how do we guarantee those step and touch voltages stay below the lethal threshold? We build a massive, invisible copper mesh buried beneath the substation, and designing this grounding grid is an incredibly complex balancing act. Engineers have to combine geological factors, like the specific resistivity of wet crushed rock, with highly complex electrical factors. They must factor in the clearing time of backup relays, just in case the primary ones fail. They calculate the system's XSR ratio, which dictates the decay of the DC offset, and they apply a decrement factor to account for asymmetrical fault currents. Every single one of these variables dictates exactly how thick the buried copper cables need to be, and how closely together they must be spaced to flatten those voltage gradients at the surface. The ultimate goal, pulled directly from the IEEE standards, is simply this: to protect human life. All of this mind-boggling math, the towering switchgear, the high-speed differential relays, the precisely sized circuit breakers, and miles of buried copper, it all exists for one single purpose: to dissipate massive energy safely into the earth so that human beings are never exposed to critical electric shock. It really changes how you look at the infrastructure around us, doesn't it? The next time you walk or drive past a massive, humming power substation, I guarantee you won't just see transformers and wires anymore. You'll know that just inches beneath your feet lies an invisible, brilliantly engineered safety net of copper and math, quietly waiting to protect us from the sheer fury of the grid. Thank you so much for joining me for this explainer. Stay curious and keep learning.